Good morning, good afternoon, and good evening, everybody, wherever you're joining us from. Thank you for joining this live stream. Today, we're going to have a very, very interesting topic that has gotten a lot of people's attention. And honestly, I'm starting to really regret making this a live stream because I think it would have been better for this to be a more structured video, given the density of the topic and, how deep or how deep we have to go to convey all of the necessary information. And it's not always great to do this type of work, after a very long day at work and doing it during the evening my time, because my brain will not be 100%. However, we're going to have a very interesting conversation about Git today that I'm sure many of you are excited about. I would love for this to be more of a two-way street conversation. So the chat is there for you and for me to engage with you. So please make sure you use it. If there's something that's off, if there's something you need more clarification about, if there's something that you need to convey to me, please do drop it in the chat. Whether you're on Twitch or on YouTube, both of these platforms have a great chatting facility. Awesome. I would love to know where you are joining me from, so let me know also in the chat. If the audio is not clear, please also do let me know. We're not going to do music today. We're just going to keep it simple. We're going to see how that goes. And whenever I'm quiet, that means I'm thinking. Use this time assume that this session is more of a workshop. If you would like to follow along and you want to, have your own setup and just do things in parallel, feel free. Otherwise, these sessions are also going to be available as recordings on YouTube, so you can come back to them at any point in time. Last disclaimer from my end, I'm not a Go expert, so I'm doing all of these live streams so that I can explore the language myself. If you see something that's off, something that could be done better, we're all learning. Just keep that in mind. Let me know about it. I'll think about incorporating it, and we'll see how we can improve things for next time. Now, let's talk about what made these episodes possible. I referenced this book in one of my short videos before, and I mentioned that this is a great reference. Okay, you're not seeing my screen. Hold on, let me switch. All right, awesome. So I referenced this book in one of my shorts before, and I mentioned that this is a fantastic reference on learning how to build Git yourself. So if you don't want to see me convey the information to you and you want to do stuff on your own, maybe do more advanced things, go and buy a copy of this book. Even if you want to follow just my series, I would highly recommend that you go and buy a copy of this book. It's a great reference. Keep it with you and support the author because he did a really awesome job. I don't know what he's doing right now. He's streaming games on on Twitch, but I don't know if he's bored of tech or something. He did a fantastic job with this book, and he has many other books. So highly recommended read. All right, I see a few folks from New York, from Saudi Arabia, from Egypt. Amazing. I love having you all here. Thank you very much for being engaged, and we are going to start right now. So I'm going to try my best in this session for us to do first a deep dive into the Git folder to understand how Git represents information on disk. It's going to be very important as a reverse engineering exercise to understand what's happening under the hood so that we can use that information in creating our own version of it. So for the first part of this session, we're going to spend a lot of time in the terminal. We're going to get familiarized with all of the notions inside the, the folders, the files, whatever is being used inside the Git folder before we move on to creating our command line interface tool. We're going to create a couple of commands that are the git init and the git commit. We're going to be doing very basic minimum implementations for these today because I need to put things into context first. And then the next parts or the following parts, we're going to go deeper and deeper until we have a full-blown implementation or as close as possible to Git within the means necessary. Now, this series is going to be probably about 6 to 7 parts. I'm not sure. It depends how fast or how much we can do in each episode. And it depends on how much preparation I can do before each one of them. Because as you know, I do this part-time and all of my weekends and my free time is spent on preparing for these things. So yeah, that's it. All right. Enough talking. Let's get started. Get comfortable. Go make yourself a nice cup of whatever you drink, coffee, tea, water, whatever, and let's get busy. So, as I mentioned, the first thing we're going to do is going to be a deep dive inside our Git repository. So, I'm going to take this gh-stars repository, which I've been working on in my previous live streams, and we're going to use this as our reference to understand what's happening inside this folder. So, this is an already existing initialized Git repository. We already, as you can see here, if I do a git log, I have a bunch of commits already in this. You can see also that I have this, I have multiple branches that have been used. I also have some tags, and I've pushed this repository previously to upstream. And by the way, I'm assuming that you already know Git, right? So I'm not gonna be starting from scratch with Git. This live stream assumes, or this series assumes, that you're using Git already, you understand Git from an end user perspective, and that nothing I'm going to talk about here should be new for you. Otherwise, you might be better off starting by learning what Git is and then coming back to the series, because this is on the more advanced front. Cool. All right, right here for me to got, so that I got this nice view, I'm using an alias that I already created. If you're not familiar with aliases, they are really good. And if you want to get the same view, you can do it this way: git log one line, not online, one line, a graph. You will probably get a similar view of this that I showed you. All right, awesome. Now, what's happening inside our Git folder? As many of you know already, Git manages everything about our files, the changes, the diffs, and whatnot inside the .git folder. Why? Because it's a distributed version control solution or tool. And by distributed, it means that you don't need to be connected to anything else for you to be able to version your changes, to pull changes, so on and so forth. And that might be confusing for many, because you might ask, well, what is GitHub and what does it mean when we're not connected? We aren't we pushing stuff to platforms like GitHub, for example, or GitLab or whatever, and pulling stuff from it? Well, yes. However, it's not necessary. These platforms are not needed for you to be able to work on your local machine and for you to be able to work on any other machine. Thank you very much, Pedro, for following. Now, you can use Git fully disconnected from any other machine, right? And this is the beauty of it. This is as opposed to, for example, Subversion. Subversion, you cannot do anything without being connected to a Subversion server. And if the server is down, all of the other nodes cannot do much anything. Locally, you cannot push, you cannot make changes, you cannot branch, you cannot do whatever. So this is the beauty of Git. Now, let's go inside the git.git folder. And I'm going to be using tree over here to really showcase a little bit of what's happening. There are a lot of files, but let's start from the top. So I'm inside the .git folder right now, and I just basically listed everything in that folder. And from the start, from the top, I mean, commit edit message is pretty much the file. It's just a single file that contains the last commit message that we had. So the last commit we did to this repository, the content of this file is going to be the message that we added to our that we added to our. All right, cool. Let me have this split screen on here so that I can also show you stuff. So let's see actually what's inside this file. And you can see here, this is just a simple message. And if I compare it to my last commit, so if I do, for example, git log, you can see here that the message of my last commit is also revert log. So this is what the file is. This is what this file is. It's pretty simple. Then we're gonna skip fetch head. We're gonna look at the head. What is head over here? And this is also a very simple file. If we look at what's inside of it, it's simply a reference to the current commit, and it can either be a commit ID, right, a hash, a SHA, or it could be a symref to the current branch, which is in this case the main branch, because this is also my default branch and the branch that I currently have checked out. Head will generally point to whatever you have checked out right now, right? So if I check out another branch, this is going to be another ref, and it's going to be a completely different value over here. Now, moving on. We have the config folder, which is where you can store a little bit your configuration. So let's see what's inside the config folder. And I'm going to explain, that folder file. And inside this config file is pretty much the configuration that is specific to this particular repository. With Git, you can have a global configuration file that applies to pretty much any repository you clone, check out, so on and so forth. Or you could have a specific configuration that is only relevant for this particular copy of your repository, right? So for example, here you can change the repository format version. I'd highly advise you not to do that. Just keep it simple. You can say if Git needs to apply the same modes of the files as per your file system, for example. So if you have file permissions that are set up, Git will just copy and replicate these file permissions. And here is where you can enable or disable that. Bare means that this repository, it signifies whether this is a bare clone or a regular clone. A bare clone pretty much is the .git folder only. This is what, so let's assume you are using a centralized repository to push and pull to, like, your upstream. It's usually a bare copy or a bare clone because we don't necessarily need to have a working copy of all of the files. So the bare clone is just simply this .git folder, including all of its content, and that's all you're going to be needing to get things moving and for things to work. All right, now also we have a bunch of other configurations, like ignoring the case, so on and so forth, some stuff that might be relevant to your operating system. It's all going to be here. And you can also see where we have the remote configurations, right? So if you add a remote to your repository, this is where it's going to go. And by remote, you can have one or many, right? You might want to pull and push from many different other origins. So you can add them here. And you have also the branch configurations. And if you have get LFS configured, this is also where you can see the LFS configuration. And again, a reminder that this configuration is only specific to this particular repository and nothing else. It doesn't apply to anything else. Now, Git description is very simple. There's not really much here that is relevant for us. It's been used by, I think, an old source management. It's called Git Web. It's like a web-based visualization of repositories and for repository management. So this contains some metadata relevant to that platform. There's not really much important stuff for us over here. Now, the hooks folder. The hooks folder is interesting because it contains pretty much scripts that you can modify to do certain actions at different points in time. So for example, if you want to, let's assume you want to check out a certain repository, and then immediately after the checkout, you want to do certain stuff like maybe removing some files, renaming some files, or I don't know, cleaning up some folders, removing some temp stuff, or generating maybe even stuff. You can use the post checkout, for example, hook to add whatever logic you want to add to the repository. And then the end user, whenever they check out a branch or they get a fresh copy of your repository, this hook is going to be called, and this script is going to be executed. And as you can see here, post checkout doesn't have the dot sample at the end. So if it has a dot sample, that means it's not going to be executed, it's going to be ignored. But if the dot sample is removed, then this script is actually going to be executed. So let's have a look at what's inside this file. And if we look at the post checkout, you will see that this is a simple bash script. Not necessarily simple, it's a bash script that it's going to do stuff. And because I have gitlfs installed and configured on this particular repository, this post checkout hook has been modified by gitlfs to do stuff for us. And as you can see here, it's just gonna push out a message saying that this repository is configured for gitlfs. And it's gonna check whether gitlfs as a command exists on this machine or not, and it's gonna give us some information about it. Cool. So these are the hooks. I'm not gonna talk more about them. You can read more about them online. They're pretty neat. Some people use them to do some local linting, verification, or maybe even, let's say, if you want to run some script before someone pushes changes upstream, right? For example, if you want to do some safety checks, or you want to do some linting work, or you want to build or whatever, you can use these hooks to execute such activities. All right, nice. We're doing well in terms of going through the content. Any questions so far? Feel free to drop them in the chat. I would love to take some of your questions and try to answer them. Now, we are getting to the interesting stuff. Let's skip index for now, just for a little bit. And you can see here, index is not necessarily a text-based file. It's more of a binary file. We're going to get to it in a bit. Let's skip it for a few minutes. And then get info. And this is something really neat. The exclude file. So sometimes you have the scenario where only on your machine, you have a file that maybe you just configure locally, like your .env or whatever. Maybe not necessarily .env, but just another file that you just need locally for you. But this file is not needed by anyone else on the team. And you don't want to add it to your .gitignore file because you don't want to pollute your .gitignore file. It's something that is very specific to you. Sorry, it's something that's very specific to you, your particular use case, your local setup, right? The exclude file over here is a perfect place to put this kind of stuff, because the exclude file isn't carried over from one copy to another. It's very limited to your local copy. You can put in whatever you want in this exclude file, and then when you push, you're not pushing these changes with, you're not pushing the exclude file with the changes. And that is a perfect way for you to have or to add any folders, files, or whatever. It behaves the same way as gitignore, but it's only local and specific for you. Now, the rest is pretty much some other metadata about the repository. This contains some ref information, not necessarily relevant for our case right now. I'm not going to go into how LFS work. Let's just skip it for a bit. LFS is outside of the scope of our conversation today. It's a separate tool, and LFS stands for Large File System, and you could use LFS. It's pretty neat because generally we don't advise anybody to commit binary files to Git. And this is a big problem from a lot of people who come from Subversion or SVN or any other version control systems. They tend to include their builds, their binaries, maybe even any other non-text file in their Git repository, and then their Git repository just mushrooms in size and becomes really, really big, and that becomes a big problem on the long run. So one of the best practices for you to do is to never ever commit binary files to your Git repository. You could use a third-party tool, not third-party. You can use LFS or Git LFS, where you can configure a repository that can store these binaries for you. So whenever you don't have to manage them differently. So whenever you do a Git add, so you stage your files, Git commit, and then Git push, the text-based content is going to be pushed to your Git repository upstream. But anything binary that you're tracking separately, like images and everything like that, is going to go towards your storage, your LFS storage, which is separate from Git. And this is the perfect solution because these storage systems are designed to manage binary files as opposed to your Git repository, which is not designed for this purpose. All right, I'm seeing the chat be quiet, so give me a signal that you're still listening and you're not really bored. And just also for me to make sure that technically everything is going well. I can see things fine, but I would love to hear from you if everything's going well. All right, now next, what do we have? We're gonna talk about the most important folder, which is the objects folder. You can see here I have a lot of objects. We're not gonna go through all of them, but I'm just gonna give you a sample. And this is the most important folder inside your .git folder. But before we do that, let's talk about refs a little bit. And refs is just a bunch of, it's very simple. Refs are, or these files contain object IDs. They contain the SHAs, they contain references to branches, they contain references to our origins, they contain references to stuff that is in our objects folder, right? That's all you need to know about it. So whenever you have many branches, they're called refs. Whenever you have tags, these are also refs. Whenever you do a git stash or git stash, it goes here. A ref is created, and a ref is basically a reference to an object that is located inside our .object, or not .object, inside our objects folder, which, as you can see here, is quite substantial. Now we're getting to the very interesting and juicy stuff, because all of this was just an introduction to talk about how Git represents objects on disk. And this is where we need to do the deep dive into the objects folder and try to understand. All right, so sorry, I'm just having a quick look at my notes just to make sure that I did not miss anything, and let's move on. So, did I talk about the logs folder? I didn't, but I'm gonna be crossing over it in a little bit. So, all right, cool. So the question is, what happens when we do a commit using Git, and how does Git store this information inside the objects folder? All right, let's have a look. So if we do a tree git/objects, you can see, sorry, I'm already inside the Git folder. So if we do, you can see a lot of files. And these files are, I'm going to explain it, and I'm going to explain something very important for you. When Git creates an object ID, which is a SHA-1 pretty much, and you would ask me, why are we using SHA-1? Because SHA is a hash function, right? And a hash function basically takes any input of any size, and it generates a fixed length identifier or string, as you can see here, that is unique for that particular combination of content. It's unique for that text, or it's unique for that input. And the possibility of having two distinct inputs generate the same SHA is highly, highly unlikely, although it's not impossible. Okay? So MD5, for example, collisions can happen. So this is what we call a collision, when two different inputs can generate the same hash. That is a collision, and that's not necessarily a good thing, because it's a problem depending on how you're using these hashes, right? So Git decided during the implementation to use a SHA-1, which is an older version of SHA. There's SHA-256 right now, which is lengthier. The number of permutations is higher. The number of combinations is bigger. So the possibility of collisions is less. Let's put it this way. However, is it really important to prevent? Great question. So Aran is asking, how does Git prevent collisions, or does it not? It doesn't. It thinks, or Git's philosophy doesn't really care about collisions, and I'll explain. For the concern about collisions, right, is that if two inputs can generate the same SHA, then some malicious actor can come in, replace a bunch of files with malicious code, and then Git will generate the same SHA for that malicious bad file, and then they will make the change and nobody will know because the SHA did not change. So there's really no way to verify that, you know, there's really no way to verify. Everybody will assume that this is the same file. However, the likelihood of that happening is very, 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 very minimal, and the SHAs in Git are not necessarily used for security purposes. They're more used to maintain the integrity of the repository more than anything else, right? That's what Git cares about. And that particular use case that I just described doesn't necessarily affect the integrity of the repository, and the likelihood of collisions is very, very minimal. Nevertheless, Git have implemented in newer versions SHA-256, but the migration to SHA-256 obviously is very slow, because if we say we're going to start adopting it, that means pretty much anyone who's using repositories need to adopt that. You have some folks who are going to remain on the older version, and they're not necessarily interested in the migration to the new version, and it's quite a big deal. So people will migrate to SHA-256 in due time, and everything that happens at the internet scale, that can take decades. I'm not really sure and confident if there's any more concrete migration plan, or if the SHA-1 is going to be deprecated anytime soon. As far as I know, there's really no effort in that direction. So now that we didn't really explain this folder structure and what it means. So whenever we commit a file or a change to Git, a SHA is generated from the content of that change. And this is pretty much the SHA that is being generated for a change. So you see the first two digits of the SHA are extracted. A folder is created with these two digits, and then the remainder of the SHA is used as the name of the file where the content resides. Now, you're going to ask, okay, great, what is inside these files then? And let's have a look. So if we go to cat object 00, and then we have this, only this file, you can see we have some gibberish that is actually spit out. If we do cat objects, I don't know, fd or b0 or b6, let's say, and then this, I also have some other gibberish, right? And this means that the content of these files is actually binary, and it's not necessarily text-based content. However, there's a way where we can really inspect what's going on and see what's in these files. I'm going to show you that right now. Okay, and nobody asked why do we split these into folders like this. The answer is very simple. Some operating systems and file systems cannot handle file names that are quite large, and they cannot handle a lot of files being in the same folder, right? So Git handles this very, very neatly by splitting these files, you know, into these distinct folders composed of the first two letters from the SHA. So this is pretty nice because then we have a pretty nice tree that is distributed, and that is we can immediately reference without doing a lot of computation. So that's a pretty nice trick for you to be aware of, and that's the reason why information or objects are split in this manner. All right, awesome. Now, how can we inspect the content of these files? Git has a very nice utility. It's called git cat file. So if I do git cat file, let's go back. All right, I can do git in anywhere, git cat file, and then -p, and then I can provide the file. So it's gonna be .git, sorry, not GitHub, objects, and then 00, and then this particular file, for example, and then oh, sorry, I have to enter the reference only, not the full path. My mistake. So if I enter the reference, which is, again, as a reminder, the first 2 digits are going to be the folder, right? And then this is the name of the file. You can see here I have this as output. What does this mean? This is pretty much the file permissions in Linux. And they are represented by so 1 represents a file, and 644 is pretty much our permissions. I'm gonna talk a little bit more about what that is and how we can see those, but let's move on a little bit from here. Then we have blob, and then we have the name of the file, right? That's being part of this object, and then we have this, and we don't really know what this is yet, and I'm gonna explain it in a little bit. But I want to show you also a different type of file just so that we can move the conversation a little bit further. I want to show you this particular one. Sorry. Let's pick another one. Let's pick, not sure, let's pick this one, B4. All right, cool. And as you can see here, this one is a bit different than the other file. This one, we're actually seeing some code. And you will ask, but Bassem, you just said these files are binary. Well, there are different types of objects that are being stored, right? So the first one we landed on is actually a tree. The second type of file right here is pretty much that we landed on is one of the files that is being staged. What I want to land on right now is to try to get to land on one of the blobs. And the reason why I want to do that is because the blobs have a very interesting structure, and they will allow us to see they will allow us to extract much more information and see how they are structured so that we can start recreating them ourselves, right? So this is another type of files that exists in our object folder. And this is also one more type. Let's have a look at this one. So all right. This is also an interesting one because this has also yet another structure. We can see a tree over here. We can see a parent, and then we can see the content. And this is the third type, which is the commit, right? This is a commit object, and you can see all of its content over here. And I'm gonna be very interested in moving along from this type of files and try to understand what's going on here. Now, the reason why we can see the content with cat file is because the content of these files is compressed using the DEFLATE algorithm. It's a compression algorithm. It is implemented with the zlib library. Git uses zlib internally, and we can find a way for us to decompress these files and see their content. So for example, this one that I wasn't able to see, I can show you right now how we can decompress it with using just regular tools. We can even do it with regular gzip. And I want to decompress it because I want to show you what the actual representation of this binary file is like after decompression. Let's do that right now. So I'm gonna do something a bit magical, but there are other ways as well. I have done this in a couple of ways. All right, I have crafted this query from before. Why? And how does it work? So first of all, we're going to be using gzip to do the decompression, right? And as I mentioned, the deflate algorithm is implemented in the zlib library, which you can use with pretty much any programming language. You can use it with Python, Ruby, Go. You can just, it comes part of the standard package if I remember correctly. Or you can just download zlib and use it to decompress. You can write the script on your own. I can show you also how you can do that with Python right now. However, you can also do it with gzip by passing this nice special header, not header, but like, the first string. I'm appending this special character string to my objects file. So I'm reading the objects file, but I'm appending this to it. So I'm reading the binary stuff. I'm appending this before that, these, hex codes. And then I'm passing this to gzip and I'm telling it to decompress this. And this should work. And as you can see here, what I got as output is similar to what my cat file has spit out, right? Are we looking at the same object? Yes. So B0 and then it ends with BE. B0, it ends with BE, right? So you can see here tree, parent, author, whatever. This is the output from cat file, and this is the output from my special crafted, decompression hacky function. And as you can see here, we have the same stuff. However, you can also see here that I have something strange appended at the beginning, and it says commit 1125. What is that? And why do we have this? Let's actually have a look at other files. What happens if we decompress other files in our folder? So let's have a look. So if I do, I don't know, D, do we have something with D? Yeah, D0, and then we decompress this file, for example. What do we get? You can see here we have tree, 3794, and whatever, and then we have a bunch of other stuff that we weren't able to actually decompress. It's still in binary form, right? So we saw the commits. We decompressed them. We got text. Perfect. Now we saw trees. We decompressed them, but still we got binary stuff. And now let's have a look at yet another object. Hopefully we will land on a blob. Let's say B6 maybe. Or no, there's no B6. B8. What's in B8? Let's try this one. No, also a tree. And don't worry, I'll clarify this in a bit. Oh, bad file. Probably a bigger tree. Let me have a look. 8.7. Yeah, maybe this one. What is this? Okay, cool. And this one is a blob. All right, awesome. Let's dig a little bit deeper to try to understand this file, right? So we saw a commit, we saw a tree, and we saw a blob. Let's see this blob and try to understand a little bit what these numbers actually mean. So this is the file. Let's copy it. Let's clear up this screen. And again, if I just read this file, you can see here, it's not readable binary, or binary compressed file, right? So if we use the compression one more time, I want to pass this to wc-c. And what wc does, it's gonna count the it's gonna count, or not count, it's gonna give me the size of the file in bytes. And we're gonna have a look at that number. So I get the number 994. Okay, great. So this number is not necessarily too different from the number that we can see over here, which is 985. 994 is not very far. And because I know this information already, I'm gonna tell it to you. Here, 985 is the size in bytes of the content that is available in this file. But 994, what we got from WC, is actually a bigger number, right? And that is because WC is accounting for blob space 985, and then we have a null character at the end. before we have the content of the file. And this is what this number here represents. It's the same for the tree, and it's the same for the commit. We have, sorry, not for the commit, for the blob, actually only for the blob. We have the size of the file in bytes that is available to us over here. So now that we understand this fact, we can have a look also at this file from another perspective and try to make more sense of it, and try to also reverse engineer it and reverse engineer the representation. Cool. Any questions so far? Anything that is not particularly clear? Any more information that you want me to provide? Please drop it in the chat. Awesome. Let's move on. Let's have a look at this file using another awesome tool, which is called hexdump. And I also promised you that you can do the compression in a different way. Let me actually show you that before you move on. Because I wrote this script that does this for me. All right, I wrote this script yesterday, I think. It's called zlib deflate, and it's quite simple. Let's have a look at it. You can write a similar script like in this manner. So you just, and this is in Python, right? Import sys, import zlib, and then you just read the content or input from the standard input, you know, read the buffer, and then just pass it on to zlib and decompress it, and just simply write the output to standard output, and you're done. That's it. If you face a problem, then you can catch the exception and throw an error. It's as simple as that. You can write the same thing with Ruby. You can write it in any other tool you like. And then what I decided to do is I wrote a fish function because I like fish. I use it as my shell. Sorry, I'm pretty sure you're not able to see the last line. Let me fix that. Also, let me hide the sticker for a little bit. I love my supporters. Oops. But let's use, I have a very limited space. Let's make use of it for a little bit. All right, cool. So I wrote a little bit, I wrote a simple fish function, and I called it zlib. And what this function does is it just simply passes whatever argument I pass to it as the argument for the zlib deflate file, Python file, and this will do the decompression for me. So instead of me typing this long, you know, command from before that prints the special character and all of that stuff, I can just simply replace that with zlib and it's gonna do the compression for me. You can do something like this yourself. So let's go back to gh and let's do zlib, for example, this, and you can see I got the content of the file decompressed and available for me. So again, commit, size, and then we have the content of the file. All right, let's have a look at these files from another angle, and let's use this time hexdump-c. And because these files were in binary, we can also see their, you know, representation over here, and it's a pretty cool representation that we have. And let's start from the left hand side all the way to the right hand side. As you can see here, we have the we have the numeric values of all the bytes, pretty much, and then we have the hexadecimal representation of each of these bytes, and then we have the ASCII representation of these files as well. And as you can see here, this is really no different than what we have been seeing when we decompress. So you can see commit 1125, and then we have tree, and then we have the content, and you can see it's pretty much what we were able to see from before. So you can have, this is an accurate representation of our content. Now, let's have a deeper look and try to sort of guarantee or decipher this a little bit. And I want to show you a couple of very nice tools you could use for this type of work. I'm also still in my terminal, and let's say I have some hex code that I want to really try to understand or, you know, look at from a different angle. You can use this tool to copy this stuff right here. Let's copy it. Let's drop it here. Let's make some changes to it. So I can take this and then I can use sed, and I can replace the spaces with 0x, right? And then I can replace this over everything, and let's see what we get. Is this enough? Let me check. Yeah, it should be good. And then we can pass this to xxd-r-p, and this will give us the ASCII representation of this chunk of hexadecimal values. You can do it for a longer string. So let's copy this and let's drop it over here. Let's remove the double stuff. And as you can see here, this is the ASCII representation. That is the same, pretty much the same as here for this chunk. Now, you can see here that this file is split into chunks of 10 bytes, right? So this is first one, this is 10, this is the second offset, 30, 40, 50, 60, whatever, right? And these are the values. This is the hex representation of these bytes. All right, awesome. I think the last piece that we have is this 471, which should give us a representation also of the size of the file that we have, right? So if we, how can we transform this into base 10? We can do the following: bash-c, and you can see me, I did this exercise before. So I can transform this into its actual value, which is 1137. And if we compare it to this, which is 1125, so 1125 is actually the content of the file without this first segment. So the first segment, if we add the bytes from the string commit space 1125, then null character, we were gonna get the same value here, 1137. Brilliant. All right, we did a lot, honestly. So we understood really how Git is stored on disk. You can pretty much use the same stuff to go and, I don't know, Splunk in your .git folder. You can play around with the files. You can see how things are on disk. So in short, Git stores these blobs, you know, as compressed binary data on disk. And if you decompress it, you're going to see it's going to start with the type of the file, whether it's a tree, commit, or a blob. And then it's going to add the size of the content of this file next to its type. And then it's going to add a null byte. And then obviously all of this data, as I mentioned, is compressed with zlib and using the DEFLATE algorithm. Now, a couple of things I want to mention also related to the tree representation, right? So we talked about blobs, but there are a couple of things regarding trees that are interesting, which I want to show you before we move on to the code in a little bit. So I already have this address stored in my notes. Let's use it. Instead of, you know, digging around and trying to find a tree, we can try to do that, but this is just faster. And again, I'm just going to pass the content of this file after decompressing it to hexdump. And let's have a look. And as you can see here, things are a bit better than just trying to decompress it. So if I don't pass this to hexdump and I just decompress the file, as you can see here, we just gibberish. We cannot really read much into it. We cannot really understand this content. But if we pass it to hexdump, it's slightly better. Slightly better. And I'll explain why. So we have, again, tree, size of the content, 457. And as I mentioned here, this is the mode, which is a signal that the next item is a file, which in this case is a .git attributes, and I know that this file exists in my repository. That's why I was able to, you know, make the link if we're gonna try to reverse engineer. And you can see in this example, for example, here it says 40,000, and I know that .github is not a file, it's a folder. So now I can, in my head, understand the distinction between these two representations in the tree. And I can see here that the file permission is 644 on this file, and it's pretty much, it's fine. Now, how can I see this in a different form? If I do a git cat file -p and then I provide this object, I should be able to see it in this form, which is what's really intended out of this, right? So the hexdump gave us some hints, and this is the proper representation. As I mentioned, and I showed you this before, this means that this is a file. These are the permissions. It also gives us the type that this is a blob, right? And here, this gives us the type that this is actually a tree, because why? This is a folder, obviously. It contains other stuff inside of it, so it has to be represented as a tree. And all files are represented as blobs. And as you can see here, these are the object IDs for each one of these files. So if I grab this object ID over here and I say git cat file -p and I pass it along, I should be able to see the content of that particular file from the object ID that I have over here. Let's do the same for this one. If I do git cat file -p and then I pass the object, you can see here this is the content of my license file. You can pretty much do the same thing. So as soon as you have an ID for a tree, you can grab it, you can cat file into it, and then you can see everything else that belongs to this tree or under this tree's hierarchy. Now, great. So Git creates a string for each one of these entries. Blobs and directories, as I mentioned, are distinguished by this one at the beginning. And yeah, that's pretty much it. There's not really much to say over here. The last experiment we want to do is to try to understand how these object IDs are actually formulated, right? Because if we do a couple of investigations, and let me show you a couple of awesome things over here. All right, the way I can get the object ID for a certain file using Git is I can just type in git ls-files, and then I can pass the file to it, and it's gonna give me, you know, this representation, which is gonna provide me the object ID as well. The object ID is supposed to be the SHA of the content of this file, right? So what happens when I do a SHA sum -a1, which means that let's use the SHA1 hashing function, and then I pass the file .gitignore, I'm gonna get something like this, which doesn't make sense. This should be equal to this, right? But why is it different? Remember that Git, how does it represent blobs on the disk? It appends to them, right? Blob and then the size of the file. So if I append this same thing to the file, what do I get? If I append blob and then the size of the file in bytes and the null byte, as I mentioned before, to the content of this file, and then I generate the SHA, what do I get? I get the same object ID as you can see from the output of ls files. And this is how SHAs are generated for or by Git. Okay, so yes, objects are blobs or trees or commits. That's pretty much the three types of objects you're going to be seeing inside your objects folder. Brilliant. I've been talking a lot, honestly. I think we're gonna move on to code. Any questions from anybody on what we talked about so far? It's pretty cool stuff. yeah, I'm not going to explain more about them because now we're going to get into the code and we're going to build them ourselves. So the code is going to explain more about these. What I wanted to do is just to show you how Git stores stuff on disk so that we can do something similar to it in our implementation, which is what we're going to try to do a little bit with the remaining time that we have together. All right, now let's go and start our project where we're going to be doing some of this work. So let me go back here to my folder and let's do one thing. Oops. Oh, that's interesting. All right. Anyway, it looks like this doesn't exist. So our implementation is going to be called G. And I don't care if you don't like it. I like it. It's not going to be called Git or anything. It's going to be called G. And we're going to start by building our code, and we're going to use a very neat library. It's called Cobra. I love it because it makes writing command line interfaces or command line interface tools so much more easier and streamlined. People don't think of it as a framework. Doesn't really matter. I mean, if it does stuff for you, and if it creates scaffolds or scaffolding code for you and things like that, it is kind of a framework, and it also dictates somewhat the folder structure. So yeah, it is a framework of sorts. Cool. Let's initialize this, and we're gonna create a new package, done, or module, and then we're going to let's open this in our VS Code. Please do let me know also if the text is small or not clear so I can zoom in. I would love to zoom the least amount possible so that I can get some nice, interesting, or decent working space. But I think this should be okay. All right. Now, the next thing we're going to do is we're going to go get Cobra. We're going to install the Cobra package. And as part of the Cobra package comes a very nice CLI tool, which we can use to initialize a new project. And I just did Cobra CLI init. And that gives us our entry point, which is the main, main.go. Perfect. And it gives us a nice folder right here, where we can include all of our commands. And as you can see, Git is, or as you know already, Git has many commands. So Git init is one command, Git commit is another command, and that's how you need to think about them. They're separate commands that have their own separate execution flows. They probably even have their own, management and release cycles and all of that stuff. I'm speculating. I don't know for sure. That's how I think about it. And they're not necessarily all codependent or interdependent. And obviously, there will be some internal packages that are used across all of these different tools. But they are sort of modularized and they're not necessarily coupled. And this is what we're going to be doing right here. So the root.go folder is pretty much going to be our main function. And as I explained in my previous series of how to build CLI tools, it's pretty neat. The main.go will pretty much execute any command that is passed. And then in the initialization, this is where we can create the flags or the arguments that we want to be able to parse and utilize in our execution for this particular command. And then the function execute is called by our, from main, by our package whenever we want to execute a certain command. And then what happens is when we create our command right here, we have an instance or a reference to the command over here. We specify it. We can create a short description for it, long description for it. And then here inside the run, we can define what happens when we call this specific command. I'm going to leave it empty for now. And let me do a quick test for you. So if I do a go build -og, and then I pass my main.go file, I should receive or have an executable. And if I run it, you should spit out the pretty much the long description over here, right? If I change the long description, compile again, and run, I should see a different value over here. I'm not gonna spend time on this stuff. I want to jump directly to creating my init. So let's do that right now. We're gonna do a cobra CLI, and then we're gonna say add init, and this is how you can create different commands. By saying add init, it's just gonna create a file inside our command folder, and here we can, you see here, this is the name of the command, and you can have a description, and you can see my run function is uncommented over here, and this is where I can do stuff. So what do we want to do in our init? In my init, I pretty much want to initialize my my repository. So this is what git init does. It creates the .git folder, it creates all of the necessary files, it creates the object folder and everything else necessary. We're gonna keep the implementation to be as minimal as possible, and we're going to start by creating just only the bare minimum files. And the bare minimum files are just gonna be the objects folder and the refs. That's what I'm gonna start with, and we're gonna add more on a need basis, obviously. So we're gonna do quickly just to define some metadata, and because I want to define the directory structure. So first of all, I'm gonna define what my metadata directory is gonna be called, and it's gonna be called g or .g. This is where I'm gonna store my information, and then I want to specify the default permissions for all of the files that are created, and I want this to be 744, and then I want to specify my content, and it's gonna be a slice of strings, and then it's gonna be, we're gonna have the objects folder, and then I want a refs folder for now. Let's keep it simple. All right, cool. Now this is complaining because these variables are not being used. We're gonna start using them right here. I'm gonna keep this. Thank you very much, Copilot. Thank you for doing my work. Let me do something for once. All right, so the first thing we're gonna do is we're gonna create the G directory with the default permissions. However, before we do that, fetch the current working directory, or for not working, current directory, and we can do that with get wd, and let's check if there's an error. And this here, pass error to standard error instead of standard output, and let's change the where we are spitting out the errors, right? And then let's exit with the code 1 in case we have an error. Why? Because we don't want to continue. And when you exit with a exit code that is non-zero, you're telling the terminal, you're telling everything else, the shell and everything, that you have a failure, you have an error. And this is how other programs can build on top of your output. These are important. These are standard, I don't know if they're standards, they're described somewhere, but this is how you need to build your, especially if you're building command line interface tools, you need to adopt these. Otherwise, people are not going to be able to use your tools effectively on all different platforms. Now, we're going to create the metadata directory inside the current directory, right? Because we're going to, the metadata directory is pretty much the .g. We're gonna create it inside there, but I don't like how this is formatted, so let's change this a little bit. String.join, and I want to join them with the path separator for, okay, let's do this. Okay, I want them to join them with the path separator for that particular operating system. And this is not necessarily correct. So let me replace this with, what is it? Path separator. Yeah. Strings.join. Yes. This is it. Oh, it's a rune, so let's cast it to a string, and this should work. Now let's replace this with our path over here, and make dir is just gonna create that directory for us, and we're gonna assume that the current directory is available and it is writable. If it's not, we're just gonna spit out an error and we're not gonna move on and proceed. I don't want to handle any other situations. This should be more than enough. Now, what I want to do next is, once this directory is created, I want to create all of the different content. And thank you very much, Copilot. It's doing my work for me. So what it does, it's doing here is iterating over the get metadata or g metadata directory, not g, sorry, g metadata directory content. And it's going to create the folder object and refs for me. So let it do its work. And then we're just going to verify. Brilliant. So path, it already inferred, you see, it's sort of copied my previous structure because this is how it thought I want things to be structured, which is great. That's exactly what I want. Strings, join, dir, get or get metadata dir, and content. Perfect. And is this really accurate? Let's see. Yes. So it's joining each one of those and using this as the separator. Perfect. And then it's just going to go and create each of these files with the appropriate permissions. And whenever it fails, it's going to exit. No cleanup. Well, I mean, I don't know of any situation where this might fail in the middle. So we're just going to assume that it is able to create all of the files successfully. But we will see. So let's print out to standard output this time. Okay, great. It's done. Initialized empty G repository. And it's funny that it picked up this message in particular, right? And then let's make sure we end with an empty, or sorry, with a new line. All right, brilliant. So I can see a few comments. I see one from Peter that these global variables should be a struct that get hydrated from flags 100%. These will definitely be moved to a configuration file that we are going to read whenever we initialize this command. But for now, let's start simple. We can always change things down the line and improve things as we go. All right, brilliant. Let's move on. Let's move on to testing this very quickly. So go build-o. Brilliant. And then let's see, do we have something in this folder? Nope. Do I have writing permissions? Yes, we should. Let's test. I hope we don't blow up the machine. And init is called initialized empty repository in this particular folder. Let's have a look. Yes, no. Well, there we go. There it is, and it has the appropriate permissions. Fantastic. And if we do a tree.g, you can see here we have the objects and we have the refs. Brilliant. All right, now we're gonna get to the second stage. And now it's gonna be funny. I want to stage these. I want to commit these files. But all right, we can do that at a later point, or at least when we have the ability to commit files. We will do it using our tools. Cool. All right. The next step is for us to write our git commit. Let's start with the basics of a git commit, but I think we're gonna postpone this to another time. And let's do what we did last time. Let's add the commit function. And let us also develop this a little bit further. Oops, sorry, wrong window. Okay. Thank you very much, everyone, for following. All right, in order for us to start working a little bit over here, we're gonna need to create a new concept of a database, right? So what I'm gonna do is I'm gonna create a new folder over here. I'm gonna call it internals. And inside this, we are going to create a new package as well as a new, set of structures. The first one is going to be our database. Why? Because I'm going to need this this definition over here to use it to maintain pretty much all of the objects that we're going to be storing on disk and to manage all of our different elements. And we're going to do, first of all, let's define this package. We're going to call it internals. And then what I want to do is I want to define a database interface. And the nice thing about Go is, unlike other languages, is implementing interfaces is quite simple. Pretty much any struct that has the methods that are defined or that has similar signatures as the methods defined for the interface implements that interface, and it can be used pretty much interchangeably with anything else that implements that interface. All right, cool. So init initializes database. I don't want to use init. I want to use new in this case, and I want it to return an error if it fails. And then I want to use store to store objects, not like that, in our database. We're gonna obviously augment this a little bit further down the line, but for now let's assume that this is what we want. And I also want to maintain the path for my database over here, and I don't want to expose the path to on the package level. I'm just gonna keep it like this, and that's the thing that threw me off at the beginning when I started using Go. If you have something capitalized, then it's exposed. If you have something lowercase, it is not, which means it's not accessible anywhere else. Now, let us implement these functions. So new over here, and then this new will be associated with this struct over here. This is going to be its own method or the method for it. And then what new is going to take as input or argument or is path. And let's fix this over here. Do we need to name things? Probably not. All right, and then it spits out an error, and then what we want to do is just specify that our local path is this one, and just for the sake of debugging or troubleshooting, let's just spit out this info. I want to use a logger, which we were probably going to implement down the line. But for now, let's just keep things simple. And let's do it like this. And in my run function, I want to create a new database. I'm not sure why this is commented out. And what I want to do from this database is I want to test out this functionality and test out the new method. So let's see, does this actually work? And what do we get? Oh, it's complaining. What is it complaining about? Oh, yeah. Let's do it like this. Keep it simple. Keep it stupid. What is it? Missing the F. All right. Go again. We're building one more time, and this time we're gonna call commit. Perfect. All right. Our scaffolding is working as intended. I definitely would like to start creating some tests for these. But I'm afraid we're gonna have to leave this for another time. Brilliant. I think I'm gonna end here for two reasons. I'm tired. It's the end of the day for me. But I also want to I also don't want to overwhelm you with information. So for now, we're just gonna stick to this. We're gonna continue in part 2 the implementation of our database structure. We are going to continue the implementation of the commit so that we can actually commit our files or this project to our tool that we're building on the fly. And we're going to store that information on disk, and we're going to store them as objects. As you've seen Git do that. Again, we're going to keep it simple. We're not going to deal with branches at the beginning. We're going to deal with that later. We're not going to deal with different arguments or parameters for commit. We're just going to, again, keep it as light as possible so that you can see this tool evolve as we go. And hopefully in the next few parts, we're going to see this grow. I'm going to do the boring stuff, like, writing documentation or changing the messages and things like that, not necessarily during the live stream, so that we can keep the live streams as information dense as possible. Mazen is asking, where will the repository for repository be? Great question. Thank you for asking. It's going to be in the glich.stream organization. However, this organization is going to be, or access to this organization is limited to my Patreon supporters. So currently this is the organization link. All of my Patreon supporters, all of my YouTube members are going to get access to this private repository. You're welcome to follow along if you would like access to the code, as well as the mind maps and the summary of these episodes, because I create mind maps for each one of these episodes with all of the information that you've just seen, structured in a way that is easily digestible with summaries. Join my Patreon, support my work, and you're going to get access to all of those. Otherwise, the live streams are going to be recorded and available for you to inspect them and follow along and build this tool or a copy or an instance of this tool for yourself. For now, I want to thank you for your awesome engagement. I want to thank you for your amazing support. I want to thank you for just being there. What do I else? I have a lot of things to thank people for. Today, someone sent me on Twitter an awesome tweet where he saw one of my tweets printed and stuck on the door of one of the companies in Lebanon. That was pretty nice to see. Again, you're all awesome, and I really hope to keep on pushing interesting content for you all. The next parts are gonna be code heavy, so we're gonna be doing much more code, less details, but I wanted to give the context for this series in this first episode. Thank you very much, everybody, for watching. I want to wish you a great rest of the day, great evening, and most likely the next episode is going to be scheduled for next week or as soon as I finish my preparations for it. Thank you very much, everyone, and I will catch you next time.